Okay, so this is a video recording for assessment 2 of PR and CV, CS 5330. So my today's topic is ALVIN. So ALVIN is basically autonomous land vehicle in a neural network. It's from 1989 and it's one of the earliest examples of a neural network steering a real vehicle directly from camera image. I will walk through the problems it solved and how the network was built and trained and why it still matters today. Okay, so why route following is hard for a robot? So driving looks easy to us, but it's a genuinely hard perception problem for a machine. Routes change constantly, lighting, surface, markings, weather. So a hand-coded rule that is like follow the white line breaks the moment the road does not have one. The car also needs a new steering decision many times per second. There's no time for slow reasoning. This is exactly the kind of a problem a learned system is suited for rather than a rule-based one. So where Alvin fits in the course. So Alvin is a classically fully connected ANN, same family as the phase detector networks earlier in the course, just applied to steer instead of detection. It actually predates both of those chronologically, but conceptually it groups with the ANN vision topics before we get into the CNNs. After this point in the course, everything shifts to convolutional and deep architectures. So think of Alvin as the last stop before that shift. So the ALVIN's architecture. So the input layer contains two sensors here, a low resolution 30 cross 32 video image that is of 960 to 960 units and a 8 cross 32 rangefinder image 256 units that gives rough distance or obstacle info. These feed into a single hidden layer of just 29 units, which is quite small by today's standards. The hidden layer connects to an output layer of 45 units. This is fully connected, not convoluted. That distinction matters because CNNs exploit spatial structure in a way this network does not. Notice the output layer has 45 units, not one. I will explain why that's a deliberate design choice in the upcoming slides. Training data simulated road generator. So the problem to train a network, you need lots of labeled examples. That is, imagine correct steering direction out. Real driving footage covering every road type and lighting condition is expensive and slow to collect. So the Pomerello's solution was to build a synthetic road generator that produces very randomized road images and automatically knows the correct steering label for each one. Since it generated the road, these synthetic images were mixed with real camera footages. So the networks are both realistic and wide-ranging examples. Once we have that labeled dataset, training is just standard back propagation, nothing exotic there. The innovation is in how the data was produced, not the learning algorithm. A curve, not a single number. So you might expect one output neuron that directly predicts the steering angle. Alvin doesn't do that. Instead of all 45 output units activate together in a smooth bell-shaped curve centered on the correct direction. The peak here represents the intended steering direction. Nearby units are partially activated too, and distant units stay almost zero. So why does this instead of one scalar? The reason behind that is a smooth distributed target is a more forgiving training signal. Small errors during training don't cause a widely wrong output, and the label itself is easy to generate for any steering angle by just centering a bell curve there from activation pattern to steering command. So given that the curve of 45 activation, the car still needs one number to actually steer by. Alvin computes the center of mass, a weighted average across all 45 units activation. That single weighted value becomes the steering curvature command sent to the vehicle. This is a simple arithmetic, but it's what turns soft distributed output into a precise continuous driving decision on the road real world results. So this wasn't just a simulation. Alvin drove NavLab aerial test vehicle at speeds up to about 55 kilometers per hour. It handled multiple road types, highways, single lane paved roads, and even unpaved trails. All of that with hand-coded lane following rules. The driving behavior came entirely from the learned network. It's worth emphasizing this was in 1989 hardware, decades before GPUs and large-scale deep learning made this kind of result uncommon. So Alvin's legacy is in end-to-end driving. So why this still matters? Alvin was a shallow network with 29 hidden units trained on a relatively small dataset using camera plus rangefinder input. Modern systems like NVIDIA's PilotNet use deep CNNs with millions of parameters trained on millions of driving frames from camera input alone. The scale is completely different, but the core idea hasn't changed. Map raw sensor input directly to a driving action through a learned network instead of hand-engineered rules. Alvin is a direct conceptual ancestor of today's end-to-end self-driving research. So the key takeaways from Alvin are Alvin was one of the first neural networks to create a vehicle directly from camera input. A synthetic road generator solved the training data scarcity problem. The Gaussian population coded output made both training and steering smoother. It's a direct ancestor of today's end-to-end self-driving networks. Thank you.